Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we will begin looking at Chapter 10, which is Stage and Continuous Gas-Liquid Separation Processes, and we will be specifically looking at absorption. So let's begin talking about how this absorption can occur. The contact between the liquid and the gas is only going to happen where these two come into contact with each other, so at the gas-liquid interface. That's the only place you have mass transfer. So what the packing is going to do is provide good mixing of this gas and this liquid. Now ideally what's going to happen is the liquid will move in really thin films over the entire packing surface, and the gas will then mix as it comes around those thin films. The most common operational problem in a packed tower is channeling. And channeling means that the liquid begins collecting into little rivulets that leave portions of the tower dry. And so the key to good design for preventing channeling will be liquid distribution at the top of the tower, and in a tall tower periodically redistributing the fluid, so collecting it and putting it back through your distribution technique again. Another practical concern is pressure drop. So the pressure drop will happen primarily because the flow through this packed layer is very tortuous, and so that will increase the fluid friction. We're going to talk about this in terms of a gas flow rate, and all my subscripts got messed up on this, so be a little bit careful here. If you have my original slides, that will probably help you. But G subscript Y is the mass of gas per time per cross-sectional area of tower. And this is going to relate to the superficial gas velocity. So this is U, let me just write this, U sub 0 times the density of the tower. And so it's just a gas flow rate, okay? It's mass per cross-sectional area. When the column is dry, the pressure drop is going to vary linearly with velocity, but when you have liquid present, it's going to be a much more complex relationship. So as the liquid holdup, or the volume of the liquid, increases, the pressure drop for the gas will increase. And there's going to be a point where the slope kind of changes, and that's called the loading point. And this is a graph. There's a great website, chemiresources.com. You should probably, add this to your set of things that you know about. But so this shows pressure drop compared to air mass velocity. And in this particular case, it's for a type of packing, which are interlocks saddles made out of ceramic, okay? And then each one of these lines here represents a different liquid mass velocity. And so if you know the gas mass velocity, okay, let's choose a number here, and the liquid mass velocity, let's go with this one here, we can find where they intersect, and that will then determine my pressure drop. Another concern is going to be flooding. Now, if you continue to increase the gas velocity, the pressure drop lines in this curve become almost vertical. And at that point, the liquid actually becomes like a continuous phase. Once the liquid becomes a continuous phase, you have something called flooding happens. And this will indeed force the liquid to begin rising, accumulating and rising in the tower. Okay? But the first sign of flooding is simply that the liquid becomes a continuous phase. You're going to recognize this when you are operating a tower, because the gas flow rate, even just a little change in the gas flow rate, causes a really huge change in the pressure drop. Okay? So what we need to do is we need to operate at a gas velocity that's lower than the flooding velocity. So we need to be able to predict this. And to predict this, we want to use delta P of flooding is this formula here, 0.115 times the packing factor to the 0.7 power. And the delta P that you're going to get from this is going to be in inches of water per foot of packing. We can do this using this graph here. Now this is viscosity, is the mu here, psi is the density of the water over the density of the liquid. F is the packing factor. We get that from the vendor, and G sub C is just the gravitational constant. And if you're using this chart here, G is going to have units of pounds per square foot per second. If you use C sub P and G sub C is 32.174. So this is a way that we can evaluate when flooding is going to occur. So we're going to stop this video here, and we're going to come back in the next lesson and look at a practical example.